September 23, 1944. 1640 hours. Hauptmann Friedrich Brenner stood behind rusted barbed wire at the prisoner compound near Thionville, France, watching 12 men accomplish the mathematically impossible. His hands gripped the fence until knuckles whitened. Before him, American engineers assembled a 42-meter bridge across the Moselle River in 7 hours and 20 minutes. According to every calculation Brenner had learned at the Technische Hochschule Berlin, according to 15 years of professional experience designing military infrastructure, according to the fundamental laws of structural engineering he had taught to junior officers, this required a minimum of 48 hours with a crew of 60 specialized personnel, heavy lifting equipment, and pre-positioned foundation work. 12 men, 7 hours, no cranes, no concrete pylons, no foundation preparation. The metallic clang of steel panels locking into place echoed across the water, like a death knell for everything Brenner thought he understood about warfare. Each section weighed approximately 270 kilograms, light enough for 6 soldiers to carry by hand. The Americans worked with mechanical efficiency, slotting prefabricated panels together like children assembling toys. No welding, no riveting. Just pins, bolts, and an elegance of design that made Brenner's throat tighten with something between professional admiration and existential dread. What Hauptmann Brenner did not know, could not know as he watched American boots crossing that bridge before sunset, was that he was witnessing the moment when Germany lost the war, not through superior firepower, not through tactical brilliance, but through mathematics applied by a civil engineer named Donald Bailey, who never fired a shot, never wore a uniform into combat, never saw the rivers his creation would cross. The bridge before Brenner represented the weaponization of simplicity itself, and it would prove more devastating than any tank, any aircraft, any artillery piece forged in the foundries of the Reich. 6 months earlier, in the frozen pre-dawn darkness of March 1944, the German defensive strategy relied on a principle as old as warfare itself: rivers as barriers. The Rhine, the Moselle, the Maas, the Roer. Each waterway represented days, sometimes weeks of delay for any advancing army. Delay meant time to reposition forces, to bring up reserves, to construct new defensive lines. German military doctrine, refined through centuries of continental warfare, treated river crossings as engineering nightmares requiring massive logistical preparation. Oberst Klaus Zimmermann, chief engineering officer for Army Group B, had quantified this advantage in a report dated March 8, 1944. Each major river crossing requires minimum 14 days preparation. Enemy forces must locate suitable crossing points, survey river depth and current velocity, transport bridging equipment forward under constant artillery interdiction, excavate foundation positions, and construct temporary spans under direct fire. Our defensive doctrine exploits this vulnerability. Current Allied advance rate, 4.3 kilometers per day. With 17 major water obstacles between current positions and German border, we calculate minimum 73 days delay factor. This provides adequate time for fortress preparation and counteroffensive positioning. The mathematics seemed irrefutable. Allied forces had demonstrated impressive logistical capabilities, true, but physics remained physics. A bridge capable of supporting 30-ton Sherman tanks required substantial engineering. The standard Allied approach used British-designed pontoon bridges, effective but slow to deploy, vulnerable to artillery, requiring calm water and favorable conditions. German intelligence had documented every Allied bridging operation since Normandy. Average deployment time, 11 days from river arrival to first vehicles crossing. 11 days multiplied by 17 rivers equaled 187 days of vulnerable positioning, except the mathematics were already obsolete. In a modest engineering office in Christchurch, England, 2 years before Brenner watched that impossible bridge rise across the Moselle, a civil engineer named Donald Coleman Bailey had solved a problem that would reshape modern warfare. Bailey possessed no military background. His expertise involved designing civilian infrastructure, calculating load distributions, optimizing material efficiency. When the British War Office requested proposals for portable military bridging, Bailey approached the challenge with civilian pragmatism rather than military orthodoxy. The breakthrough was almost absurd in its simplicity: modular panels. Each panel measured 3 meters by 1.5 meters, constructed from high tensile steel in a lattice pattern that distributed weight with maximum efficiency. 10 standard bolts connected each panel to its neighbors. No welding required. No specialized tools. No engineering degree necessary for assembly. 6 men could carry one panel. 12 men could assemble a bridge. The elegance resided in the mathematics. Traditional military bridges used fixed designs, each structure custom-engineered for specific spans and load requirements. Bailey's system was infinitely scalable. Need a longer bridge? Add more panels. Need higher load capacity? Stack panels vertically in double or triple configuration. Same components, infinite applications. A single design that could cross a 6-meter stream or a 60-meter river gorge. But the true genius, the element that would prove strategically decisive, was speed. Lieutenant Colonel David Henderson, British Army Engineering Corps, witnessed the first full-scale test in May 1942. His official report, dated May 19th, captured his astonishment. Observed construction of 30-meter Bailey Bridge by single engineering platoon. 12 enlisted men, 1 sergeant supervisor. No heavy equipment employed. Panels transported by standard lorry, assembled on near bank, pushed across span on temporary rollers. Total construction time, 6 hours 47 minutes from first panel placement to first vehicle crossing. Load test successful. Bridge supported 40-ton Churchill tank at full speed with 0 structural deflection. Recommend immediate mass production and deployment. This system will revolutionize military engineering doctrine. Henderson's recommendation proved conservative. The Bailey Bridge would not merely revolutionize doctrine. It would obsolete the entire concept of rivers as defensive barriers. By September 1944, as Hauptmann Brenner stood watching that bridge rise across the Moselle, Allied forces had deployed over 3,200 Bailey bridges across Europe. 3,200 rivers crossed. 3,200 defensive positions bypassed. 3,200 opportunities for German forces to establish killing zones, to channel Allied advances, to extract the brutal arithmetic of delay and attrition, simply nullified by modular steel panels and 10 standardized bolts. The production numbers told their own story. British and American factories manufactured Bailey Bridge components at a rate of 180 complete bridge sets per month. Each set could span up to 60 meters. Total monthly production capacity, 10,800 meters of bridge. German bridge production, hampered by material shortages and Allied bombing, averaged 14 permanent bridges per month, requiring specialized construction battalions, heavy equipment, and weeks of labor per installation. The disparity was almost obscene. For every meter of German bridging capacity, the Allies produced 771 meters of Bailey Bridge. A ratio of 771 to 1. But statistics remained abstract until they acquired flesh and consequence. Brenner first understood something fundamental had changed on August 27, 1944, though he did not yet comprehend what he was witnessing. His engineering company, attached to the 7th Army defending against Allied advance from Normandy, had destroyed the bridge over the Marne River at Château-Thierry, a textbook example of defensive engineering. The stone bridge, originally constructed in 1728, featured 3 massive arches spanning 82 meters. German demolition charges had dropped the center span into the river, creating an impassable obstacle. Current velocity measured 2.8 meters per second, depth averaging 4.2 meters, banks rising at 37-degree angles, approaches offering excellent fields of fire for German artillery positioned on the eastern heights. They will need 2 weeks minimum, Brenner had told his commanding officer, Oberstleutnant Werner Baumann. The span is too wide for pontoon bridges in this current. They must construct a temporary span, which requires foundation work in the river itself. Our artillery will interdict any engineering work. 2 weeks, probably 3 before they can bring armor across. 41 hours later, American Sherman tanks were crossing the Marne. Brenner had heard the reports with disbelief verging on anger. Impossible. The physics did not permit it. He demanded to inspect the site personally. Convinced the reports reflected confusion, perhaps a ford discovered upstream, perhaps light vehicles only, certainly not armor, certainly not in 41 hours. What he found defied his professional reality. The Americans had not attempted to repair the destroyed bridge. They had not constructed foundations in the river. They had simply assembled a Bailey bridge on the western bank and pushed it across the span like extending a telescope. The entire structure rested on the original stone piers at either end, requiring no preparation, no foundation work, nothing but the assembly of prefabricated panels. The bridge stood complete, functional, supporting tank traffic at 10-minute intervals. Gefreiter Hans Becker, one of Brenner's surveyors who had observed the construction through field glasses from concealed position, recorded in his diary, August 28th, watched Americans build bridge at Chateau Thierry. Could not believe eyes. Assembled on bank like erector set. Pushed across river on small wheeled carriages. When far end reached opposite bank, they removed carriages, bolted bridge to old stone supports, and tanks were crossing within the hour. Counted sections as they assembled them. 83 identical panels, 12 men doing the work. We destroyed that bridge with 200 kilograms of explosives, thinking we had bought 2 weeks. They replaced it in less than 2 days. How do we stop an enemy that can cross any river in 40 hours? How indeed? The question haunted Brenner through the chaotic retreat of late August and early September. Each destroyed bridge, each blown culvert, each demolished viaduct represented hours of German engineering effort, careful placement of demolition charges, precise calculation of structural weak points, dangerous work often conducted under fire. And each obstacle delayed Allied advance for approximately 48 hours before a Bailey bridge appeared, as inevitable as sunrise. The strategic mathematics became a nightmare. Germany's defensive doctrine assumed river lines would provide cumulative delay, each obstacle adding days to Allied timeline, allowing German forces to rest, refit, and establish new positions. But if each river represented only 48 hours delay instead of 14 days, the entire calculation collapsed. 17 major water obstacles multiplied by 14 days equaled 238 days of defensive advantage. 17 obstacles multiplied by 2 days equaled 34 days. The Allies had compressed 7 months of defensive warfare into 5 weeks, and they had done it with modular steel panels designed by a civil engineer in Christchurch. By mid-September, Brenner's engineering company had been reduced to 22 men from its original complement of 114. Not through combat casualties, though those had been severe enough, but through simple mathematics of retreat. Units fragmented, supply lines collapsed, organization dissolved into chaos. When American forces surrounded Thionville on September 19th, Brenner found himself commanding 7 engineers, 2 trucks with no fuel, and enough explosive charges to destroy one final bridge, a narrow span over a tributary of the Moselle. They detonated the charges at dawn on September 20th. The bridge collapsed into the stream with satisfying completeness, stone and timber churning the water into foam. "That will buy us 6 hours, Brenner told his men, knowing he was lying, knowing even as he spoke that 6 hours was optimistic, knowing that somewhere behind Allied lines, a Bailey bridge set was already being loaded onto trucks. 4 hours and 17 minutes later, American soldiers were crossing on a Bailey bridge. Brenner and his men surrendered at 14:30 hours. There seemed no point in anything else. You could not fight mathematics. You could not combat the weaponization of simplicity. You could not win a war against an enemy who had solved the fundamental equation of military engineering. The prisoner compound at Thionville held approximately 800 German soldiers, a mixture of combat infantry, support personnel, and engineering units captured during the encirclement. Conditions were adequate. Food rations sufficient if monotonous, medical care available for wounded, shelter provided in requisitioned French barracks. American guards maintained professional distance, neither hostile nor friendly, simply executing procedures. But for Brenner, the barbed wire might as well have been constructed from his own obsolescence. The compound overlooked the Moselle River, which meant he could watch hour after hour, day after day, as American engineering battalions demonstrated the capabilities he had once thought impossible. September 22nd, they assembled a 38-meter bridge in 9 hours. Brenner counted panels through the fence, 76 standard sections, double-stacked for heavy load capacity. The bridge supported continuous traffic. Sherman tanks, tank destroyers, supply trucks, jeeps, artillery pieces, 10 vehicles per hour, every hour, flowing east toward Germany. Each vehicle represented another increment of defeat, another factor in the mathematical certainty of German collapse. Oberst Martin Kessler, senior German officer in the compound, a career engineering officer who had designed fortifications from Norway to North Africa, stood beside Brenner at the fence on the evening of September 22nd, watching American trucks cross the latest Bailey Bridge. Kessler was 57 years old, his face carved into permanent creases by 3 decades of military service, holder of the Iron Cross First Class from the previous war, author of the standard Wehrmacht manual on field fortifications. He watched the bridge in silence for 11 minutes before speaking. "Do you know what frightens me most, Hauptmann? Not that they can build these bridges so quickly. Any nation with sufficient industrial capacity could manufacture portable bridge components. What terrifies me is that they thought of it first. This Bailey design represents a fundamental reimagining of military engineering. Modular, scalable, simple enough for common soldiers to assemble, strong enough to support heavy armor. We Germans pride ourselves on engineering excellence, on technical sophistication, on solving complex problems through precise calculation and superior design. And a British civil engineer with no military background defeated our entire defensive strategy by making bridges simple." Kessler paused, and when he continued, his voice carried the weight of comprehensive defeat. "We built Tigers and Panthers, magnificent machines, engineering marvels that required 18 months to produce and a doctorate to maintain. They built Shermans, adequate tanks in overwhelming numbers. We developed V-2 rockets, technological breakthroughs that represented the future of warfare. They developed Bailey bridges, boring rectangles of prefabricated steel. And they are winning, Hauptmann. They are winning because they understood something we did not. In total war, simple solutions deployed in massive scale defeat complex solutions deployed in limited numbers. Always, without exception." The words settled over Brenner like ash from burned cities. He had spent 15 years mastering the complexities of structural engineering, learning to calculate stress distributions in 3-dimensional matrices, designing bridges as unique solutions to specific problems. Each bridge he had designed was a custom creation, optimized for its particular span, load requirements, and environmental conditions. He had taken pride in that complexity, that specificity, that craftsmanship. Bailey had simply made rectangles that bolted together. And Bailey had won. September 23rd brought the moment that would crystallize everything Brenner thought he understood about warfare, engineering, and the mathematical certainty of defeat. At 1400 hours, an American captain entered the compound, accompanied by 2 guards and a translator. The captain was perhaps 32 years old, medium height, unremarkable features, the kind of officer who managed logistics rather than led charges. He carried a clipboard. "I need engineers," the captain announced in accented but functional German. "We're constructing a bridge over the main channel tomorrow. 47-meter span, triple-stacked configuration for railroad conversion. I need 40 German prisoners with engineering or construction experience. You'll work under American supervision. Full rations, medical care if needed. Anyone who refuses will simply remain here. Anyone who works will receive Red Cross documentation noting cooperation." The calculation was transparent. Work or don't, your choice. The bridge gets built either way. Your participation merely reduces American labor requirements. Brenner felt 53 pairs of eyes turned toward him and Kessler. The decision belonged to the ranking engineering officers. Kessler met Brenner's gaze, and something passed between them that required no words. This was the final humiliation. Not merely to be defeated by superior engineering, but to be conscripted into demonstrating that superiority, to become instruments of their own obsolescence. "We will work," Kessler said quietly. The translator raised an eyebrow. "All engineering personnel, I only need 40 men. All 53 of us will work," Kessler replied. "If you are going to teach us the future of military engineering, we might as well learn the lesson completely." September 24th, 0600 hours. 53 German engineers stood in formation on the western bank of the Moselle, while American sergeants distributed tools and explained procedures in mixture of English, German, and universal gesture. The Bailey Bridge panels were stacked in neat rows, each stamped with identification numbers, each identical to every other panel in the formation. Technical Sergeant Robert Morrison, a construction foreman from Pittsburgh in civilian life, provided the briefing. Each panel weighs 270 kilos. That's 6 men per panel. Use the carrying handles. Panels slot together with 10 bolts, locations marked in red paint. You can't screw it up. We're building triple stack configuration, which means we assemble 3 layers vertically for maximum load capacity. Bottom layer goes together first. We push it out over the water on launching rollers. Then we add second and third layers while the whole thing rests on temporary supports. When we reach far bank, we anchor it, remove the rollers and temporary supports, and we're done. Questions? Brenner raised his hand. How long? Morrison checked his clipboard. Last triple stack 47-meter span took 11 hours, 14 minutes. We're shooting for under 11 hours today. You boys work hard. We might hit 10.5. 10.5 hours for a bridge that would have required Brenner's pre-war engineering firm 8 weeks to design and 6 months to construct. The disparity was so vast it became almost abstract, a number too large to carry emotional weight. They began at 0632. The work was physically demanding but mentally simple, exactly as designed. 6 men lifted each panel by its built-in handles, carried it to the assembly point, positioned it according to the sergeant's directions, and inserted 10 bolts through pre-drilled holes marked in red paint. Tighten with standard wrenches. Move to next panel. Repeat. The simplicity was almost insulting. Brenner had spent 4 years at university learning stress analysis, material science, structural dynamics. He could calculate the harmonic resonance frequency of suspension bridges, design arched spans that would endure centuries, optimize material distribution to minimize weight while maximizing strength. And here he was, following instructions so basic that a child could execute them, assembling a bridge that would carry 40-ton tanks across a major river. By 0900 hours, they had completed the bottom layer. 37 panels, stretching from the western bank, pushed out over the water on small wheeled carriages. The structure looked impossibly delicate, a metal framework so full of empty space it seemed more air than steel. Brenner's engineer's eye automatically calculated the load capacity, the stress distribution, the deflection under weight, and reached the conclusion that this bridge should not work. But it did work. They added the second layer at 11:15 hours, bolting it directly atop the first, creating a structure with double the load capacity. The mathematics were elegant in their brutality. Each layer added proportionally increased the bridge's strength-to-weight ratio, an optimization that Brenner recognized as genuinely sophisticated engineering disguised in simple execution. Gefreiter Otto Schmidt, a structural engineer from Bremen who had designed factory buildings before the war, worked beside Brenner positioning panels. As they tightened the final bolts on a second layer section, Schmidt spoke quietly. "Hauptmann, I have been calculating the load distribution. This design is brilliant. The lattice pattern distributes stress vectors across the entire panel surface, eliminating point loads. The modular system means you can scale to any length without recalculating the entire structure. And the assembly method requires no specialized knowledge because the design incorporates error correction. The panels only fit together one way, impossible to install incorrectly." This Bailey engineer, whoever he was, understood something fundamental about design philosophy. "What?" Brenner asked, though he already knew the answer. "That the best solution is the one that works every time, not the one that works perfectly once. We Germans design for optimal performance under ideal conditions. This Bailey Bridge is designed for adequate performance under any conditions. And adequate performance deployed universally defeats optimal performance deployed rarely." They completed the third layer at 15:47 hours. Total construction time, 9 hours, 15 minutes. The bridge stood complete, a triple-stacked marvel of modular engineering capable of supporting railroad locomotives, tank transporters, any load the Allied logistics network required. American engineers conducted immediate load testing. A 42-ton tank destroyer crossed at full speed. the bridge deflecting less than 3 centimeters under maximum load, well within acceptable engineering tolerances. Brenner stood at the western approach as American vehicles began crossing at 16:40 hours, exactly the same time he had been watching the previous bridge construction 24 hours earlier. The symmetry was not lost on him. He had become a witness to his own obsolescence, repeated daily, made inevitable by mathematics and modular steel panels. Major Charles Henderson, the American engineering officer overseeing the project, approached Brenner as the German prisoners were preparing to return to the compound. Henderson spoke adequate German, studied at Heidelberg before the war, carried himself with the casual competence of someone who understood his technical superiority required no assertion. "You're Hauptmann Brenner, correct? Technical University Berlin, class of 29, thesis on load optimization in arched spans?" Brenner nodded, surprised. "You have access to German academic records?" "We have access to everything," Henderson replied without arrogance, simply stating fact. "Your thesis was actually quite good. I read it during my postgraduate work. Your calculation method for three-dimensional stress distribution in non-uniform arch geometry was elegant." "Thank you," Brenner said reflexively, then immediately felt absurd thanking his captor for complimenting academic work that now seemed utterly irrelevant. Henderson seemed to read the thought. "It's not irrelevant, Hauptmann. Sophisticated engineering still matters, but war has a way of reducing everything to the simplest functional form. Bailey's Bridge isn't sophisticated, not by the standards you and I learned. It's just simple enough to mass produce, simple enough to transport, simple enough to assemble, and strong enough to win. Sometimes simple is its own form of genius." Brenner gestured toward the bridge, where an unending line of American vehicles continued crossing toward Germany. "How many of these have been built?" "As of last week's logistics report, 3,247 Bailey bridges deployed in European theater. Average construction time has dropped to 7.2 hours for standard single-lane configuration. We're crossing rivers faster than your forces can blow the bridges. We're crossing rivers that don't have bridges, just assembling Bailey spans wherever we need them. We've essentially eliminated water obstacles as a defensive barrier. Your Oberkommando based its entire defensive strategy on river lines buying time for repositioning. We've compressed that timeline from months to weeks." Henderson paused, and something almost sympathetic crossed his face. "The cruel mathematics, Hauptmann, is that you would have thought of this eventually. German engineering is exceptional. Your technical universities are world-class. Your industrial capacity was formidable before the bombing campaign. In a different timeline, maybe German engineers develop modular bridging first, and we're the ones standing here watching our defensive strategy collapse. But Bailey thought of it first, and in total war, first-mover advantage is everything." The conversation haunted Brenner through the remainder of September and into October. The prisoner compound at Thionville held him for 6 weeks before transfer to a larger facility in northern France, then eventually to England for the duration. The war ground toward its inevitable conclusion, each day bringing new reports of German collapse, each week carrying new evidence of mathematical certainty transformed into historical fact. But what stayed with Brenner, what he turned over in his mind through months of captivity and years of reconstruction afterward, was the fundamental lesson encoded in those modular steel panels. That warfare had been revolutionized not by sophisticated weaponry, but by simplified logistics. The side that could move supplies fastest, cross obstacles quickest, adapt to changing conditions most efficiently, possessed an advantage that superior tactics or better equipment could rarely overcome. The numbers supported this with brutal clarity. Post-war analysis, conducted by military historians with access to German and Allied records, revealed the strategic impact of Bailey bridges in quantifiable terms. Allied forces in the European theater constructed 3,872 Bailey bridges between June 1944 and May 1945. Total combined length, 137,400 meters of bridge. Average construction time, 7.4 hours per bridge. German forces, during the same period, managed to construct 214 permanent or semi-permanent military bridges. Average construction time, 18 days per bridge. Total combined length, 7,100 meters. The ratio was 65-1 in favor of Allied bridging capacity. 65 meters of Bailey Bridge for every meter of German bridge construction, and this disparity directly translated into operational tempo. Allied forces maintained average advance rate of 6.8 kilometers per day across European theater. German operational planning had projected Allied advance rate of 3.1 kilometers per day, based on historical analysis of river crossing delays. The difference between projected and actual advance rates, 119% faster than German planning assumed. And that difference, compounded across 11 months of operations, across hundreds of river crossings, across thousands of tactical decisions based on assumptions of delay that never materialized, meant that the war ended in May 1945 instead of sometime in 1946, saving hundreds of thousands of lives and preventing a potential nuclear weapon deployment against German cities. One man's design. One civilian engineer's application of modular simplicity. Strategic impact equivalent to entire army groups. Oberst Kessler, who survived the war and returned to Germany in 1947, wrote in his memoir published in 1953, "We lost the war in countless ways, through strategic errors, resource shortages, political insanity, and moral bankruptcy. But among the purely technical defeats, nothing symbolized our failure more completely than the Bailey Bridge. We Germans prided ourselves on engineering excellence, on precision and sophistication. Donald Bailey defeated us with rectangles and bolts. The lesson is eternal. In war, the side that reduces complexity to functional simplicity will defeat the side that mistakes complexity for superiority. We built Tigers when we needed trucks. We built V2s when we needed Bailey bridges, and we lost." Friedrich Brenner was released from British custody in March 1947, returning to a Germany that existed only in fragments, a landscape of rubble and reconstruction. He resumed his engineering career, initially working on bridge reconstruction, ironically enough, later teaching at the rebuilt Technical University of Berlin. He never designed another custom bridge, never returned to the sophisticated stress analysis and optimization techniques that had defined his pre-war career. Instead, he taught simplified modular design, advocating for standardized components and rapid assembly techniques. His colleagues sometimes questioned this approach, arguing that German engineering tradition emphasized craftsmanship and optimization. Brenner would smile at such comments and direct their attention to a small object on his office shelf. A single panel from a Bailey Bridge, approximately 1 meter by half a meter, recovered from a demolished span during reconstruction work in 1948. This panel, he would tell skeptical students, represents the most important lesson of modern warfare, that elegance resides in simplicity, that sophistication means nothing if it cannot be deployed, and that the best solution is always the one that can be executed by ordinary people under difficult conditions. I spent 15 years learning to design complex bridges that required teams of specialists to construct. This panel can be installed by 6 soldiers with wrenches. Learn from my defeat. In 1968, Brenner attended the dedication of a war memorial in Thionville, invited by the French government as a gesture of reconciliation. The memorial stood on the western bank of the Moselle, near the location where he had watched, 24 years earlier, 12 American soldiers accomplish the mathematically impossible. The memorial incorporated an actual Bailey Bridge span, preserved and mounted as sculpture, a 42-meter section arching over a reflecting pool. During the ceremony, Brenner met Robert Morrison, the American technical sergeant who had supervised German prisoners in bridge construction, now a retired contractor living in Pennsylvania. They stood together before the preserved Bailey span, 2 elderly men contemplating a monument to their younger selves. "Did you ever meet him?" Brenner asked. "Donald Bailey?" Morrison nodded. "Once, briefly, in 1951 at an engineering conference in London. Quiet man, modest, seemed almost embarrassed by the attention. I told him his bridge probably shortened the war by 6 months. He said he'd just been trying to solve a problem efficiently and was pleased it had been useful." "Useful?" Brenner repeated, and something between a laugh and a sob escaped his throat. 3,800 bridges, 137,000 meters. The difference between victory and defeat. and he considered it useful. What else would you call it? Morrison asked gently. Brenner thought about this for a long moment, watching sunlight reflect off the preserved Bailey panels, seeing in their latticed structure the same impossible elegance that had defeated him and his nation. I would call it the purest expression of engineering philosophy ever deployed in warfare. To reduce a complex problem to its simplest functional form, to create a solution so robust that ordinary soldiers could execute it under fire, to scale production so massively that the solution became inevitable rather than exceptional. That is not merely useful, Sergeant. That is genius disguised as simplicity. In the decades following, Bailey bridges remained in military service worldwide, with over 300 still in use for permanent civilian infrastructure as of the early 21st century. The design saw action in Korea, Vietnam, the Falklands, Iraq, Afghanistan, anywhere military forces required rapid river crossing capability. Engineers modified the original design, improved materials, added innovations, but the fundamental principle remained: modular panels that bolted together, simple enough for common soldiers, strong enough for any load. Donald Bailey himself, the civil engineer from Christchurch who never wore a uniform into combat, who never saw the rivers his creation would cross, who simply applied mathematical simplicity to military complexity, received a knighthood in 1946. He died in 1985 at age 83, having witnessed his modular panels deployed on every continent, having seen his simplified design become the international standard for military bridging, having lived long enough to understand that his rectangles and bolts had changed warfare as fundamentally as any weapon ever forged. Friedrich Brenner died in 1992 at age 87. His obituary in German engineering journals noted his contributions to post-war reconstruction, his advocacy for simplified modular design, his influence on a generation of engineers who learned to value functional simplicity over complex optimization. But the obituary made no mention of September 1944, of standing behind barbed wire watching impossibility become routine, of the moment when a career officer trained in sophisticated engineering understood that he had been defeated by elegance itself. That Bailey bridge panel remained on Brenner's office shelf throughout his teaching career, then was donated to the Technical University Berlin Engineering Museum after his death. It sits there still, mounted in a display case with a small placard. Panel from Bailey Bridge, circa 1944. Weight, 270 kilograms. Assembly time, 12 minutes with 6 personnel. Strategic impact, incalculable. Donated by Professor Friedrich Brenner with the note, "The best weapon is the one that makes war shorter." Students pass this display daily, most barely glancing at what appears to be a mundane fragment of military equipment, a rectangle of steel latticework notable primarily for its ordinariness. Few recognize what they are seeing: the weaponization of simplicity, the strategic deployment of mathematical efficiency, the physical embodiment of the principle that in total war, simple solutions executed universally defeat complex solutions executed rarely. The panel weighs 270 kilograms. It requires 6 soldiers to carry. 10 bolts connect it to adjacent panels. With these panels, assembled by ordinary personnel under combat conditions, Allied forces crossed 3,872 rivers in 11 months, compressed 7 months of defensive warfare into 5 weeks, advanced 119% faster than enemy planning projected, and shortened the most destructive war in human history by an estimated 6 months. Not through superior firepower, not through tactical brilliance, through modular panels that bolted together. Donald Bailey changed warfare without firing a shot. He defeated German engineering excellence with functional simplicity. He revolutionized military doctrine by making bridges boring, and in doing so, he proved the fundamental theorem of total war, that the side which solves logistics defeats the side which perfects tactics, always, without exception, eternally. The lesson stands, mounted in a museum display case, waiting for the next generation to learn what Friedrich Brenner learned in September 1944. That war is mathematics, that complexity is vulnerability, and that sometimes the most devastating weapon is the one that simply works, every time, everywhere, executed by ordinary people doing extraordinary things with simple tools. The panel weighs 270 kilograms. It won a war, and it never fired a single shot.